Good afternoon, everyone. My name is Dr. Seshadri, working as professor in Institute of Aeronautical Engineering, Hyderabad. Today, I want to discuss about losses in a DC machine. So, the course title is DC Machines and Transformers. Course objectives: the students will try to learn the elementary experimental and modeling skills for handling problems with electrical machines in the industries and domestic applications to excel in professional career. The operation of DC machines and its role in power transmission and distribution. The intuitive knowledge needed to test and analyze the performance leading and design of electric machines by conducting various tests and calculate the performance parameters. Coming to the course outcomes, at the end of the course, students should be able to analyze the performance characteristics of a DC machine under various loading conditions, determine the critical field resistance and speed of DC shunt generator using open circuit characteristics, examine the performance of DC shunt machine with the different speed control techniques and predetermine the efficiency, estimate and separate the core losses in DC machine by conducting a suitable test, and finally examine the performance and speed control of DC machines using simulation tools. Coming to the losses in DC machine, we know DC machines can be a generator or DC motor. DC generator is nothing but it converts mechanical energy into electrical energy. A DC motor is nothing but it converts electrical energy into mechanical energy. So here input is electrical, output is mechanical. Coming to the DC machine. So input is electrical and output is mechanical, but in between input and output there should be losses because the machine consists of rotating parts. So it is a rotating device. The induced EMF in DC generator is dynamically induced EMF, and here it is having rotating parts. So definitely there should be mechanical losses and rotational losses, everything. So coming to the losses in DC machine, losses can be classified as core losses and copper losses. Okay, so core losses are iron losses and copper losses. And total losses in a DC machine can be classified as electrical or copper losses, core or iron losses. Also having brushes, so the brush contact drop should be there. So that losses also called as brush losses. And mechanical losses, the rotating parts, frictional windage losses. So coming to the magnetic losses and mechanical losses are all combinedly called as stray load losses. Stray load losses. So mechanical losses may be friction and windage losses. So these are the classification of losses. So first one, electrical or copper losses in DC machine. Coming to these losses, also called as winding losses. Winding losses. As the copper loss occurs because of the resistance of the windings. Whenever a current flowing in the winding, definitely the winding having a resistance. So square of the resistance is called as copper losses. Copper losses, also called as winding losses. Then the ohmic loss is produced by the current flowing in the windings. The windings that are present in addition to the armature windings are nothing but field windings. So I square RSS means the field current, shunt field current losses, and I square RSC is nothing but the copper losses in the series field winding. Also, interpoles and compensating windings also having some losses. So armature copper losses in general are I square R, where IA is armature current and RA is armature resistance. These losses are about 30% of the total full load losses. Only copper losses are 30% of full load losses. But in a series machine, the copper loss in series windings is I square RSC, Eddy square RSC, I square RSC, where ISC is the current through the series field winding and RSC is the resistance of the series field winding. So these copper loss in interpoles windings are written as I square into interpole resistance, where Ri is the resistance of the interpole winding, and copper loss in the compensating winding, if any is there, also we can compensating winding losses also. So where RC is the resistance of compensating winding. And next, magnetic losses or core losses are iron loss and dissipations. The core losses are two types: hysteresis and eddy current losses. So these losses are considered almost constant as the machine are usually operated at constant flux density and constant speed. So these losses are about 20% of the full load losses. Copper losses are about 30%, and iron losses are about, or constant losses are about 20% of full load losses. And brush losses in distribution. Brushes means here we are using carbon or graphite brushes. So two brushes will be there. Brush losses are the losses taking place between commutator and the carbon brushes. It is the power loss at the brush contact point. The brush drop depends upon the brush contact voltage drop, also called as BCD, and the armature current IA. So it is given by the equation EG equal to V plus IARE plus ISCRSC plus brush contact drop. This can also be considered while calculating the generating EMF. The voltage drop occurring over a large range of armature currents across a set of brushes is approximately constant. If the value of brush voltage drop is not given, then it is usually assumed to be about 2 volts. Thus, the brush contact drop is taken as 2 into U. So, 2 volts generally it is the brush contact drop. Mechanical losses in distribution. The losses that will take place because of mechanical effects of machines are known as mechanical losses. These mechanical losses are divided to bearing friction losses and windage losses. The losses occurring in the moving parts of machine and the air present in the machine is known as windage loss. These losses are very small. So, and stray load losses in distribution. So, these are miscellaneous type of losses. The following factors are considered stray load losses: the distortion of flux because of armature reaction and the short circuit current in the coil undergoing commutation. These losses are very difficult to determine, therefore it is necessary to assign the reasonable value for stray load losses. For the most machines, stray losses are taken by convention to be only 1% of full load output power. And efficiency. Efficiency is simply defined as the ratio of output power to the input power at R equal to total resistance of the armature circuit. And if we consider the brush contact resistance at series winding resistance, interpole winding resistance, and compensating winding resistance, these are all to be considered as a total resistance R. And the efficiency of generators is explained as SUM is equal to output power by input power. So here the power flow diagram is given for analyzing the losses. So here losses, total losses are iron losses and copper losses and some mechanical losses and also small amount of losses due to stray load. So whenever if you are considering a generator, we are giving input from a prime mover, and after the losses occurring, the available input is given at the shaft, that is electromagnetic power, and after detecting the copper losses at the rotor, and the output is given, and again after detecting the armature terminal power or series field losses or shunt field losses, final output will become. So this output is nothing but the electrical output. So electrical energy is the output. The total copper losses are I square R8, T means total, and power loss in the shunt circuit V into ISH, and mechanical losses are friction losses plus windage losses at commutator, and core losses are hysteresis losses plus eddy current losses total. Stereo losses are magnetic losses and mechanical losses are called as core losses. And the sum of shunt field copper losses and shallow losses may be considered as combined fixed losses that do not vary with the load current I. Therefore, constant losses for both the shunt and compound generator equal to slave load losses plus shunt field copper losses. So, total losses are copper losses and shunt field copper losses. Eddy current losses. So, when a conductor cuts a magnetic field, the EMF is induced according to Farada's laws of electromagnetic induction. So, this way, when the armature rotates in the magnetic field, an EMF induced in it. So, but an additional EMF induced in the laminated core also. So, although the amount of additional EMF is very small, it drives high current, which is known as eddy current, because of the low resistance of core, as the area of the core is comparatively high, large enough. So, eddy current losses are directly proportional to the frequency square. So, here W is the eddy current losses, Vmax maximum flux is 10 Weber per meter square. Frequency in H, Weber per meter square Tesla. Frequency in H, width of the lamination meters, volume in cubic meters. So, as the formula shows that the eddy current losses are directly proportional to the square of the width of each lamination. Thus, it can be minimized to reduce the size of laminated core. By reducing the laminated core, we can reduce the eddy current losses. So, eddy current losses can be reduced by using laminated silicon steel or high grade silicon steel, or low reluctant, low hysteresis constant. So, generally it is silicon steel material. So, both hysteresis and eddy current losses are constant. Hysteresis losses can be reduced by using the silicon steel material. So, by hysteresis and eddy current losses are constant, both are constant in the shunt and compound mount generator. But as the field current is almost constant in these type of generators, so these losses are again 20 to 30% of total load loss. So, we'll see one problem related to the losses and efficiency. Here, given a power transformer has a core material for which hysteresis coefficient is 120 joules per meter cube and eddy current loss coefficient is 250. Its volume is 10,000 cubic centimeters and the maximum frequency is given as 1.18 into Weber per meter square. We also call it Tesla. The core is built up of the thin laminations of thick 8 meter, thickness 8 millimeters, thickness millimeter. Width of the thickness meters are millimeters, no problem. And what is the total iron or core losses in the watts? In watts. If the frequency of the alternating current is 50 Hz. So, given frequency is 50 Hz here, and hysteresis constant is given as 120 joules per meter cube, and values, if we substitute all these values, after substituting, we can calculate the hysteresis losses. KH is given and Vmax power also is given, frequency of is given, and V volume. So, volume is 10,000 cubic centimeters. So, if you convert all these into CGS quantities, we can get the expression, we can get the value for hysteresis losses are as 78.19 watts. And the eddy current losses given by, we have formula for this also. Eddy current losses are directly proportional to the square of the Hysteresis laws are directly proportional to frequency, and eddy current laws are directly proportional to square of the frequency. So after substituting all these values here, Ke is given as 250 and Vmax value have 1.18 Tesla and F square 50 H square and T square 8 milli uh, and T 10 power volume 10,000 cubic centimeters. So we have 0.057 watts. So therefore the total core losses are hysteresis losses 78.19 and eddy current losses 0.557 and total iron losses are calculated as 78.747 watts. And coming to the final problem, in a 250 kVA transformer, the iron losses is 250 watts and the full load copper losses are given as 400 watts. Find the efficiency at full load at 0.8 power factor lagging. But we have full load output power as given as 25 kVA. So 25 kVA, we should convert this kVA into kilowatt by just kVA into cos phi gives kilowatt. So here 25 kVA and power factor given as 0.8, so we can get it as 20 kilowatts. So this is the output power, and total losses given as full load losses 400 and iron losses 250, total 650 watts. And these 650 watts can be converted into 650 by 1000 equal to 0.65 kilowatt. And full load input power equal to total output power plus losses. So input equal to 2.65, and we have efficiency formula that efficiency equal to output by input. Output is, we have calculated output power 20 kilowatt and input power as 20.65 kilowatt. So output power by input power is, we can calculate efficiency as 96.85. So the efficiency, we calculate the efficiency for a transformer because it is a static device. We don't have any rotational parts, so transformer will get maximum efficiency. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.